In this review problem, we're going to talk about finding the Laplace transforms of these piecewise defined functions. For number one, we have sine of t when t is between 0 and 2 pi, but is equal to 0 when t is greater than or equal to 2 pi. So for number one, first there's the brute force way of getting the Laplace transform, and that's by directly doing the integral. Integral from 0 to 2 pi, e to the minus st times sine of t dt, plus integral from 2 pi to infinity of 0 times sine of t dt. Clearly, the second integral is equal to 0, and so this could be just simply written as integral from 0 to 2 pi e to the minus st times sine of t dt. And then we can look this up on the table of integrals and get it. That's one way of doing the problem. Here's a second way of doing the problem, and that's by rewriting this function here in terms of the unit step functions. So we see that f of t is equal to sine of t times, let's say, g of t, where g of t is equal to 1 if t is between 0 and 2 pi, and 0 if t is greater than 2 pi. So I can factor the sine t out, and then I have a 0, 1 function. Okay, so for this function, it starts off at 1, and then at time 2 pi, I take a step down of size 1, and then it stays at that level thereafter. And so I can simply write the function f of t as this, or sine of t minus sine of t times u of 2 pi of t. Now, for this problem and for this problem only, I will use the periodic properties of sine. So I'm going to make the second part of this more complicated by writing this as sine of t minus 2 pi times u of 2 pi of t. Now, the reason I will do this is because I have a formula for the Laplace transform of something that looks like this. So if that's my function f of t, then the Laplace transform f of s is going to be, well, the Laplace transform of sine of t is simply 1 over s squared plus 1. Then if I have sine of t minus c times the unit function, step function at c, this is going to be equal to e to the minus t times c, or s times c, pardon me, over s squared plus 1, which is 1 over s squared plus 1 is, again, the Laplace transform of sine t all by itself. And so this simplifies as 1 minus e to the minus 2 pi s over s squared plus 1. And so that is the Laplace transform for this first function. For the second function, problem part 2 here, we have that we want the Laplace transform of t u6 of t. Now, again, ideally, if I had t minus 6, like that, u6 of t, I know how to find the Laplace transform of this because I have the 6 here and also the shift t minus 6 here. Now, obviously, I'm not done writing. I need to write this as Laplace transform of this. Then I have to add on the extra 6 that I left off. Okay, now the Laplace transform of 6 times the unit step function, that's going to be just e to the minus 6s times 6 over s. So the e to the minus 6s comes from the step function. The Laplace transform of 6 is 6 over s. To figure out the Laplace transform of this part, we remember that the Laplace transform of t is 1 over s squared, and therefore the Laplace transform of this is going to be over s squared, but I'll have an e to the minus 6s on top. And so getting the common denominator, we get e to the minus 6s, it factors out, everything over s squared. I get 6s here and then plus 1 there. And that is the Laplace transform of this function. And just a refresher, this function here, just to see what it looks like, okay, up until time 6, it's 0. So up until time 6, it's 0. And then from point 6 onward, the graph looks like y equals t. So this is a discontinuous function that I'm modeling with this shorthand. Finally, the last problem. The Laplace transform of e to the 5 minus 3t times u4 of t. So the Laplace transform of e to the 5 minus 3t times u4 of t, like this. Now once again, ideally we'd like to have a t minus 4 up here, so I'm going to force that. So what I'm going to do is write this as Laplace transform of e to the minus 3 t minus 4, like this, u4 of t. Now let's work out the arithmetic. If I were to multiply this out, I'd have e to the plus 12. I need e to the plus 5. So I have to multiply this by e to the minus 7 to make this work out. So by the law of exponents, I would have e to the 12 times e to the minus 7 gives me e to the plus 5. And then e to the minus 3t matches this part. Okay, to find the Laplace transform, recall that the Laplace transform of e to the minus 3t is 1 over s plus 3. And so therefore the Laplace transform of this will be, well, I've got the e to the minus 7 in front. Then I have over s plus 3 like before, but instead of a 1 on top, I now have e to the minus 4s, where the 4 comes from the step function 4 here. And so I can write this a little bit better. That's going to be e to the minus 4s minus 7 over s plus 3. And that is the Laplace transform of this discontinuous function.